I'm Marla Diaz, and we are presenting problem 1 from homework 3. I'm here with Eric and Alexander. Next slide, please. So our problem statement. So we have to use the big M method to find the optimal solution to the following linear program, and we also have to verify the solution using Cplex. Our objective function is minimizing z equals negative 3x1 plus x2, which is subject to x1 minus 2x2 greater than or equal to 2, and x1 plus x2 greater than or equal to 3. And the x1 and x2 have to be greater than or equal to 0. So to apply the big M method, we need to convert the inequalities into equalities by introducing slack and artificial variables. So we will need to turn the equalities into standard form. So for x1 minus x2 greater than or equal to 2, we introduce a slack variable, which would be e1, and an artificial variable would be a1. And for negative x1 plus x2 greater than or equal to 3, we introduce a slack variable, which is e2, and an artificial variable a2. So the system of equation becomes x1 minus x2 minus 2x2 minus e1 plus a1 equals to 2, and negative x1 plus x2 minus e2 plus a2 equals to 3. All the variables, static variables and artificial variables, and the x1 and the x2 are greater than or equal to 0. Next slide.
So since we introduced artificial variables to our constraints, we're minimizing z, we need to add ma1 and ma2 to our objective function, where m denotes just a very large number. So this changes our objective function, and it now becomes z is equal to negative 3x1 plus x2 plus ma1 plus ma2. Continuing on, we need to remove the a1 and a2 variables from the objective function. So we perform some simple algebraic operations where we add m times row 1 and m times row 2, and thus becoming our objective function of z plus 3x1 plus x2 times negative m minus 1 minus me1 minus me2 is equal to 5m. Putting this into our initial tableau, we get the following, where we have our basic variables of z, a1, a2, following our z, x1, x2, e1, e2, a1, and a2 values for each objective function and constraint, our right-hand side as well. And then we can perform our simplex method, where we find our greatest m value, most positive value in our objective function, which here would be x1 is equal to 3. And then we can perform our ratio test of taking the right-hand side of our constraints divided by the column of x1. And we get that the row 1 is going to be the leaving variable. So x1 will enter and a1 leaves. And then once that is done, we follow the steps in the previous slide, performing the following row operations, where we take row 0 and subtract 3 times row 1, and row 2, we add row 1 to it, and we obtain the following tableau.
And to further on this method, we will have x2 be entering the basis for the next tableau. And to be able to do this, we need to, in row 0, we add row 0 plus m minus 5 times row 2, and then row 1 is row 1 plus negative 2 times row 2, and then in row 2, we do negative 1 times row 2. We attain the following tableau, which will be the final tableau that we need. And here we get that the x1 will be negative 8, the x2 will be negative 5, and the z-score will end up being 19. And we also decided to do Cplex code as well to enter this in to see what it gets. The code is on the left side where we put in the objective function and the constraints as well. And then the solution it gave was negative 8 and negative 5. But in conclusion, as these are negative numbers, these fail the ratio test and they're negative, and thus they are not part of the, they don't comply with the non-negativity constraints. And so this would not be a feasible solution to this problem. Thank you for your time. That is our problem.